Hello, everyone, and welcome to the expected value lesson in the probability chapter. Today, we're going to be able to calculate, interpret, and apply expected value. And expected value is really important with probability, and businesses use this to make decisions. Okay, a lot of times it's focused on how do I make the most expected profit based on the situation that I'm given. So let's start like we always do with a warm up. Okay, what's the probability of rolling the standard die 10 times and getting exactly 2 rolls of the number 5? Pause the video, think about what we've learned so far that'll help you do this. When you're ready, unpause the video and we'll take a look. Okay, so in one of the last lessons we learned about binomial experiments. This is an example of it. Okay, we got the set number of rolls. We want exactly 2 successes. We know the probability of success is 1 out of 6. There's only 1 5 on a die, and there's 6 total possibilities. So probability of success 1/6, probability of not success is 5/6, and we can put it into our formula. So there's about a 29% chance that if we roll a die 10 times, we're going to get exactly 2 5s and 8 others. Now today we're going to take and we're going to use more binomial distribution, and it's going to help us find expected value. An expected value is, in the simplest terms, it's a weighted average. What's the average outcome that will happen? We're going to use the concepts of mean and average to help us start figuring out the formula for expected value. So let's explore. The company has 20 employees whose hourly wages are shown on the bar graph to the right over here. An employee is chosen at random. What's the probability that his or her hourly wage is $12, $25, $50? I'm going to write a probability distribution here. We're going to find the mean hourly wage. And then we'll discuss, is the mean a good way to figure out the typical hourly wage? So go ahead, answer these 3 questions, pause the video, think about what do we remember about mean, what's the probability of each event happening, and then part C is really come up with your argument of, is the mean an okay measure of center or not? Okay, so probabilities. It says there's 20 employees, so that's probably going to be my denominator. Okay, I write down each probability of $12 an hour. I count 14 out of 20. If you didn't count 14, it's completely okay. I know bar graphs are sometimes hard to read if they don't have the tick marks, and that's why we should make accurate graphs. I simplify it down to 7 over 10. Probability that person makes $25 is 5 out of 20 people, and then the probability that the person makes $50 is 1 out of 20. Now we remember that mean is we add up all of the salaries and we divide by how many people. Now, hopefully you didn't fall into the trap of, well, there's 3 different numbers, so I do 12 plus 25 plus 50 divided by 3. We need to weight the averages, so we need to do 14 12s. Now, if you wrote 12 plus 12 plus 12 plus 12, you wrote 14 times, okay, that will work. But that's just a lot of work. Okay, it's a lot of writing, and we don't really want to do that, so we use multiplication to represent lots of addition. We have 14 12s, we have 5 people that make $25, we have the CEO or whoever, the head honcho, makes $50. We add them up and we divide them by the 20 people. And we get $17.15 as the mean hourly wage. Now, is the mean a good description? I wouldn't say so. I would probably say no in this case. Most people, 14 out of 20 people, make $12. So you can't say that the average worker makes 17. The average worker makes 12. But these will skew the data. Okay, this person is like 4 workers in one. He's making 4 times what the $12 per hour worker is making. So a lot of times the mean, if we don't have outliers, is great. It's definitely a data point, but in this situation, I'd argue that mean not so good. But this idea of mean is going to help us figure out expected value. So the expected value is the average outcome with many trials. Okay, it's a theoretical outcome. If we do an infinite or a really large amount of trials, we can use a formula and use a weighted average, say, and take each event, each outcome, and multiply by the probability of that outcome, and then we take the sum of the entire expression. So we have outcomes x1, x2, x3, all the way up to xn. We can have as many different outcomes as we want. And we need a probability for each one. So that's why the probability distribution is going to come into focus. So if we know the outcome, we know the probability, we multiply them together, and we add all of those to find the grand sum, which is the expected value. So here's an example. Table shows data on sales in 1 month for each item on a restaurant menu. So restaurants serving soup and stew and lasagna and chili. Sounds like a pretty good restaurant to me. To estimate the future profits, the owner evaluates the average profit for each meal. Okay, and they want what's the average profit that the owner can expect to make from each meal. When they say expect and probability, we're probably using expected value. And then I want to know the expected profit for the next 200 meals. So when you go ahead, pause the video, write down what you think you should do, then check in. I'll show you a step if that'll help you to finish the problem. Okay, so we have learned expected value, and it's pretty new to us, but we see that we take the outcome, which is make 34 cents for the stew, and multiply it by 12% of the time. So that's going to be 12% of our total expected value. Now we're going to do that with every other event. So if you haven't done that with all the other events, okay, I would like you to write those out. Pause the video if you need. And here we go. We take a look. We say 7% of the time we're going to make 41 cents, and 45% of the time we're going to make 64 cents, and 36% of the time we're going to make 73 cents. And we're going to add them all together. And I really would like to do that on a calculator or something that can compute faster than I can. Multiplying decimals we can do, but there's no need for us to do it by hand. So my expected value is 0.6203, and decimal keeps going. Well, actually, decimal stops there. But now I want to interpret it. It says it's the average profit. So let's write that as money. So 62 cents per meal, or 62-cent profit per meal. It's not 62%. We need to always identify what did we just find, because now we can see, hey, it makes sense. More of the meals are down here and have higher profit, so 62 cents seems reasonable. Now the expected profit we can make, if we make 62 cents per one meal, we can multiply by 200 meals. And we could say that in 200 meals, they're going to make $124.06. Now that seems kind of low, but they're also selling very cheap items. But if I take my expected value for one event, I can multiply by however many trials I have and say, I expect this much. Does not mean it's exactly how much it's going to have. Okay, maybe I have a sports team that really likes chili and everyone orders chili. Then my actual profit goes up. But my expected profit is based on the averages and based on the percents. Now, here's some theoreticals where we have to think. Less calculation, but we still got to understand what these situations are saying. So what would happen to the expected value if fewer people order the chili and more people order the stew? Go ahead, answer it, write down your thoughts. When you're ready, unpause the video. Okay, so looking at this example, okay, if the higher profit item So we sell less of that, and we sell more of the cheaper item, the expected value decreases. So this is what companies have to figure out. How do we sell more of our higher price item so that we make more profit? Now, suppose the owner of the restaurant increases the order of the stew by 5 cents and decreases the order of the chili by 5 cents. What happens? Now we see the expected value once again is going to decrease because there's more orders of this, more orders of chili than there are of stew. So 12% of the time we're going to get 5 more cents, and 36% of the time we're going to get 5 less cents. So changing the profit or the outcome will also change the expected value. So anytime something changes, I probably would just recalculate the new expected value. And you might have done that in these two. You might have said, well, the expected value we saw was 62 cents, and each time my new expected value changed. Now, expected value also can be used in carnival games. In this example, a charity is considering a fundraiser event in which donors pay $1 to spin the wheel 3 times. And what's the expected payoff? Okay, so you spin the wheel 3 times. If you get 3 even numbers, you win an item worth $4. If you don't get 3 even numbers, you lose. So I want you to be very careful when you try this. Think about what are the possible outcomes, what are the probabilities of those outcomes, and find me the expected value. So first, find me the expected value for the charity. How much is the charity going to make or lose? And then what's the expected value for the person who plays, the person who's making the donation? Pause the video, take a few minutes, try this out, and we'll see if you get it right. Okay, so here's the big hint I'm going to have, and you may want to pause the video and try the problem again. So the two outcomes, okay, either the person can win and have a net of $3, or the person can lose $1. Because if the person pays $1 and wins 4, they have an outcome where they win 3. Okay, wants the payoff. So if you had 4 and -1, you may want to change that slightly in your equation, and we'll see how that applies. So pause the video if you need. If not, here comes the explanation. So the spinner's independent events, okay, I can use that just to multiply each outcome. The probability that it lands on an even is 1/2. Half of the numbers are even. So the probability that the person wins is 1/8. Half times half times half. Now, like I said, the charity can either lose 3 if the person wins, or the charity can get $1 if the person loses. So 1/8 of the time, the charity is going to lose $3 because the person's going to win, and 7/8 of the time, the charity is going to win $1. So overall, the charity should average gaining 50 cents per person. Now, if we look at it from the person's point of view, the reverse is true. They win $3 1/8 of the time, they lose $1 7/8 of the time. So they should expect to lose 50 cents each time they play. Now, they can't lose 50 cents. They're either going to lose $1 or win 3. But on average, if they do thousands of trials, they play the game thousands of times, every time they should expect 50 cents less than what they had previously. And that's expected value, taking all of the outcomes, multiplying each outcome by its probability. And in the next lesson, we're going to do more expected value.